more quicker at deposits. And so you have scale deposits in geysers, for example, that are significant. That's starting to take the volume of your water that you're trying to store. It scales around your thermostat, so you can't regulate temperature anymore. Your geyser just carries on heating up because you can't sense.
Even in the boilers also.
Correct.
In kettle, tea kettle.
Yes.
When we add the water.
Yeah. So whether it's a kettle or whether it's an industrial sized boiler, it's still important.
Heat exchangers.
But for this scaling, we normally go for the descaling process.
So we were just talking about that. So the descaling process, you can stabilize it, so you don't have to physically descale every once in a while. So by doing that, you're not going to have this anymore. So you don't have to, you can choose.
But
some people would just rather plan maintenance, we replace pipes.
But normally it's for the inlet water, you can see if we increase the temperature, there is always a scale. That's why we go for the descaling always. It's for the normal routine process.
So you should measure your hardness. If your hardness is around 80, that's where you want it to be. If it's too soft, it's going to be corrosive. So then it's going to eat these pipes. That's also a problem because then the water leaks. You lose pressure. And it becomes just as much as a problem. But look at this. 70%, 40%, that's significant cost. And so municipalities, councils that are distributing the water should stabilize the water so that this cost of replacing your toilet flush and your geyser and your kettle and blah 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 at home shouldn't be your cost. You're paying for water that should be of a certain quality, that should be non-scale forming.
Which is more cost effective, the descaling process or for the we should go for the softening of the water before?
I think you need to look at the entire life cycle cost in terms of descaling against putting this in as a once-off process and cost. I can't tell you what it is. You need to go and do that exercise because this is a certain cost. The cost is going to vary on what the quality of this is. The impact of the scale forming is also going to have this is going to influence that. So if you manage this, what is the cost? What are you going to save in terms of your descaling? Go and do the exercise. There's a classic chemical precipitation process. So it's the same sort of thing as we've been talking about. Coagulation, settling, filtration. Pre-treatment by aeration. We can pre-treat here as well. Remember I was talking about pre-treatment, aeration, ozonation, anything like that. Why do we want to pre-treat? Pre-treat is going to mean savings here. Mean savings in chemical addition. Go and do the exercise. I can't tell you what is going to be cheaper for you. I can say to you that it's worth doing the exercise. Depends on the quality of the water, the source of the water. Groundwater has got lots of typically manganese and iron in it. So there you want to pre-treat, you can oxidize that out quite easily. You want to pre-sedimentate. If it's high turbidity, again it influences this. So, like I said, magnesium and calcium are the two major culprits associated with this. We precipitate by increasing pH. We then apply conventional processes to remove that, or to induce the precipitation, I suppose. It falls out, we settle it. If we need to filter it, we can. Normally we add a CO2 to lower the pH again. Because yeah, we're increasing pH, allowing it to precipitate. The more we increase pH, the more we're going to precipitate out, right? I think there's a slide on that. Let's just see what happens here. There we go. So not only calcium, magnesium, here's some other typical parameters that you can start looking at removing. If you've got color in your water from a textile effluent point of view,
Yes.
you can look at chemical precipitation of that. Can't give you the answer right now, that's the detail. We can engage in the detail. pH becomes important. And this is why. So for typically, calcium precipitation, pH of 10. Magnesium, 11. Those are high. Arsenic, higher than 10.5. Total organics and color as we increase the pH. Do the jar test. That's going to be how much depends, how high pH depends on concentrations of this and how much you want to achieve at the end. And then we start getting into some serious contaminants that we can remove through precipitation, through pH increase. And I'm skipping through these because we're not talking the detail. So we've got sludge that's coming out of there, remember. The same with ion exchange. What is ion exchange? You familiar with it? That's what it is. It's an interchange of cations and anions in a media. We call it resin, a bed of certain charge. So if you want to remove salt, sodium chloride, you put it through a specific resin that's charged accordingly, and then when the water goes through the resins, they swap each other out. In fact, I've got a little slide showing it. Let's not try and explain it. So water softeners are a good example of ion exchange. And in households, we have these little things under the counters are water or ion exchange. And like I said, it can, like with chemical precipitation, ion exchange can also remove other elements as well, commonly. So it's passed through this bed of resin. There's a certain mixture of resin. There's certain types, different types of resin, depending on what you want to remove and what your water quality is like. When that bed of resin becomes saturated, you need to stop the process. So this is what happens. You have a column with resin in it, you feed it. As over time, as it starts exchanging, your column gets saturated to a point where it breaks through. So now you're not getting any more treatment, and you have to regenerate that. So when you regenerate it, you generate a brine. Sorry, you were going to say something?
Yeah, regenerate the resin.
Yeah. So you've got to add a regenerant to the process to then return this back to this active resin media that you can reuse. So you can reuse the resin. It doesn't last forever. The company can come and fetch it and take it away and regenerate it for you and bring it back, depending on your appetite for operation. The fact of the matter, for the purposes of these 2 days, is that we're generating a waste solution that's not clean water. Yes, we've got clean water, but we've got a separated brine as well. There's solids, to call it that. Concentration of salts that needs to be disposed of. So what I would like to just point out here is that there's a certain affinity selection process that the resin offers for certain elements. So in anion resins, nitrates, chloride are selected first. So you may, if, for example, if you want to remove a hydroxide or fluoride or whatever for whatever matter, you probably, if there's nitrates and chlorides in the water, they're going to be removed first. So you're going to have to do that, so you just treat that. Or you can get a more specific resin these days that will target that specific element as well. And it's the same for the cations. So there you can see sodium chloride is fairly high up in the order of removal of these materials. So demineralization is, you can achieve, what's demineralization?
The removal of minerals from.
Lots of salts. So down to 1 to 10 TDS. So you can just pass the same water through a couple of ion exchange columns to demineralize it. You can distill it as well, I guess, but yeah, horses for courses. Were you going to ask something? No. So that's a classic little, what we call water softener. So the water's passing through there, that's your brine tank, and when this column gets saturated, we regenerate it. Okay, so they can be automated and controlled, so there's not a lot of input that's required, so they become very popular because of that interface. So that brings us on to membranes, I suppose, if we're okay with the concept of ion exchange. This is just talking concepts, by the way. So in our desire to start removing salts, we went back to basics, I suppose, in osmosis and reverse osmosis. And we quickly realized that if we use a membrane that's got very small openings in it, and we apply pressure on that, we can force the water through the membrane and leave the contaminants behind. What is the difference between microfiltration, ultrafiltration, nanofiltration, and reverse osmosis?
In microfiltration, monovalent, divalent, and virus can pass.
So what does that mean?
It means that holes of membranes are big than reverse osmosis.
Only because of the size of the contaminations.
It depends upon the holes in the membrane.
Yeah, size.
So we know that all four are
Water
membrane
molecule can
applications.
pass in all these.
The point I'm trying to make, maybe it's not directed at you guys because you've got some knowledge, all of you hopefully are membranes, is that people often just apply RO because they only think RO as a membrane option. They don't realize that there are other membranes available for different applications. And the RO membrane sellers don't always tell them that because it's more expensive to put in an RO membrane. And so I see a lot of RO being applied where it's not necessary. So that's the concept. I think you're very familiar with that. I want to rather just, so there's a good illustration as to the different membranes and what it allows through. And it's a function of how much pressure you put on the membrane, right? The more pressure, the more gets squeezed through the membrane. The more your removal efficiency. So this slide is maybe a bit misleading here in terms of saying we get pure water coming out.
In reverse osmosis membrane, water molecule only pass.
Yes.
Other are rejected.
So if you only want to remove suspended solids, no cations or anions, you don't have to use reverse osmosis.
Yes.
You can use microfiltration. etc., etc. So what, and like I said to you before, in the 60s in South Africa, we went, RO, yes, this, and we realized it was expensive. But we realized we needed to pre-treat the water because this water must be of a certain quality that you put on the membrane. And so pre-treatment with another membrane is normally quite a good idea. So you can remove, you get a lot of bacteria contamination on your membranes, etc., etc. Some of the ions are not good for your membranes. There's been a lot of work on membranes. I'm not going to go into the detail of it now, but this is a useful guide. It's a relatively old document as well. It's also from the Water Research Commission, but it's available if you need some more reference on desalination. That just puts it in a different perspective in terms of the size of the different particles that you may want to remove. How they are made up, and of course these days there's a lot of development on forward osmosis as well. So taking a brine solution and putting it through a membrane. So brine treatment, we'll talk about it just now, is starting to use forward osmosis or regular osmosis as we know it. Remember reverse osmosis, we're putting pressure on the membrane and we're pushing the material through it. Regular osmosis is relying on a high concentration, low concentration interaction, the movement of salts through a membrane. Fouling on membranes is quite an important aspect. A lot of this becomes residual that ends up in your sludge or your precipitate or your material for disposal, your solids to call it that. And there are various ways to manage fouling, etc., etc. Like I said, pre-treatment is quite important. Again, pre-treatment is going to generate some more material that you need to dispose of and manage. We'll get to, and that's just an indication of cross-flow filtration membranes relative to direct filtration. So again, efficiencies, cost, you look at all of that. These are the big ones, small ones, they come in all sizes. I'm going to carry on. I think there's a slide on, there it is. Right. Let me just go back. I think there's a duplication here that's no. So we'll come back to that just now. We'll nominate who's going to sit where for lunch, just by the way. Let's carry on a bit because we've got a little bit of time. If you guys are okay with that. So this is what we're going to end up with in membrane applications and in brine. And there's some useful references available these days and a lot of research being done on brine disposal. Because we've also realized that for, in particular, seawater reverse osmosis, where it's certainly quite popular, and if you look at a map showing seawater reverse osmosis installations, there's a massive concentration of it around the Gulf and around that part of the world. Huge. I think the UAE is in desperate need of it. But it's growing worldwide. But the discharge of the brine typically back into the sea is fine. What is sea concentration salts?
about 20,000.
About 20 to 30,000 ppm, depending where you are. What can the concentration of the brine be?
Concentration of brine?
Yes.
Around 70-80%.
So it depends on your recovery rate.
Yes.
But yes, typically, so that's significantly higher than the 20,000. So when you look at it from a discharge point of view, it has an impact in the sea, on life in the sea, the ecology, I guess, of the sea, if you have this 70, 80,000 TDS concentration deposit there, and they're starting to realize that the coral is being destroyed and some of the big undersea forests, the seaweeds and all these things are being impacted on. And even in the small islands, holiday resorts, where each hotel has got its own little desalination plant now, their brine disposal is starting to have a concentrated effect on the corals in the Seychelles, Mauritius, Caribbean, all these places. So there's a need to start managing that a bit better. No more of this just throwing it away. So the brine is influenced by these factors. Obviously, the quality of your feed water is a 30,000, 20,000. What else is in there? What pre-treatment process are we using before that? Doesn't necessarily mean there's going to be less solids to dispose of. The type of desalination process these days, and how much water do we want to recover from that process? 50%, 60, 70, 80%? So there's a trade-off with that and the cost, of course. Because remember, the more pressure, the more recovery, the more pressure, the more cost. Electricity consumption, bigger pumps, etc., etc. And then your post-treatment solution, dilution, maybe not. So here's an interesting table that just gives us some perspective, I guess, in terms of that concentration factor for the brine. The higher the recovery, the higher the brine. So there's a correlating concentration factor that you can apply. So if your TDS is 10 and you want 50% recovery, you can get 20 TDS in your brine, for example. And the higher you go, obviously the higher the concentration.
Is it possible to run 100 to 1000 cycle of concentration?
Is it possible to run 100 to 1000? What?
Cycle of concentration.
That's not the cycle,
Concentration.
that's the concentration factor. So your recovery there is 99%. So you're really pushing your
Is
your
it possible for seawater?
Yes, you can do it in stages. So that will be a cumulative effect. Why is it not possible?
Money should be there.
Dollars should be there. Dollars. Is it necessary is my question.
It contains very high TDS. Very high.
Yeah, but so what, do you want to drink the water?
Oh, I can.
How much of that do you need to drink? If this has got TDS of 1, is that good for us?
No. We add actually some salts as well there.
Crazy, hey? You put this under huge cost treatment and then we need to add salts to it because our body needs minerals. So that's why they make some of this to a certain quantity and they take your other water and they say, okay, now you can drink it. Now it's got the right balance. This on its own, not only that, your corrosiveness, because you've taken all the salts out, becomes the water quality from your stability point of view. And then you can't go add chemicals to that now to stabilize it, because you're now going to affect the taste. So it becomes tricky from that point of view. So they tend to rather make up a certain amount from drinking water. Industrial application different. And so we have a matrix of different options from a brine disposal application point of view. This is quite general, and we'll go into some of the details of some of these things perhaps after lunch. And again, it's budget appetite, it's what is your regulatory requirement, what tertiary or downstream activities are available, to benefit from this? Have you got farmers that you can give the salt to the animals to eat the salt, etc., etc.? Is there a salt manufacturing facility? Chlorine manufacturing, etc., etc. We'll touch on some of that just now. So there's lots of options, is what I'm saying. And so there's no option. You can't say, oh, we can't do anything, we'll just throw it into the environment, just pump it. Yes, some of them cost money. So we've got to look at this final end destination, I suppose. What is that final purpose? What can be very simple. We might want to recover the salt. We want to maybe use that brine for industrial applications. And we may want to recover metals. So those are all things that are around these days. There's been a lot of research. I found a very useful research document on this, which I've shared. So a lot of this is based on that paper that I've come across. I'm certainly not an expert in brine treatment, but suffice to say that I'm the engineer, not the chemist. But you have a whole lot of different processes, from just using the natural sun and evaporation through to rather complex concentrators and crystallizers and the likes to remove this material, evaporators. And so this paper that I'm going to reference to, this one, is based on some of that. Let's carry on.
Brine is also used for chlorine.
Yes, chloralkali, we'll talk about it. So if we want to use the sun and just use evaporation, we can do that. It works quite well. It's obviously very restricted in terms of your presence. I think, yeah, or maybe Lahore was nice and cool this last couple of days. And obviously, winter it's nice and cool. Summer it's hellish hot, right? Is that right? But there's a change in your evaporation, I suppose.
May and June, the hottest day of course.
Yeah.
But it is
So
not
we have
visible near sea water, because humidity is high in that area.
So we have the same in South Africa. Our east coast is quite humid. So Durban area, it's got the warm Indian Ocean, and we have a lot of evaporation and humidity there. It's tropical. On the west side of South Africa, we've got the cold Atlantic Ocean. So it's not as humid there. There are no mountains, so you don't have this cloud formation which is contributing towards the humidity that we have in the east. And it can get to 35 degrees. Inland in Johannesburg and in the central areas, 40 degrees in summer, but dry. Rain, yes, but not humidity. And in winter down to 0, maybe -5, coldest. But just for a short, just in the morning, overnight, by midday it's warmed up to 15 degrees. So this is very site specific is what we're saying. And if you've got space, you can do this because we're just relying on the sunlight. Obviously the salt is left behind and we can remove it. They're easy to construct and have very little maintenance and operational input. I'm reluctant to say little maintenance because in my experiences, little maintenance becomes zero maintenance very quickly. And even evaporation ponds or ponds in water treatment processes need some attention. A septic tank is another good example of a process that you check it every once in a while and then you forget about it, and eventually it contributes to a big problem. So one of the big challenges with these is the lining, I suppose. That can become quite expensive. Plastic lining that you need to put in to protect the groundwater interface, this groundwater pollution. There we go, liners. And they need to be UV protected as well. It's no good they're putting them out in the middle of the desert and a year later the sun has destroyed them and they disappear. Depending on how you're going to get in to take your brine out, if you're going to access with mechanical means, mobile lifter of sorts, you need to protect your lining as well. So there are various types of linings you can get. You can maybe have a concrete base for that and have sides that are plastic, depending on cost analysis again, what's cheap and what's most appropriate, I guess, for your application. Bentonite is another clay type of material that's quite good at sealing, and you can use it as a liner. These clay liners. Overall, my impression is that over time these things tend to self-seal anyways. But the regulator may not allow you to adopt that approach to say, well, it's going to take 3 or 4 years for the thing to become sealed on its own, because you're going to have this residual accumulation in it. By that time, the groundwater's been contaminated, and if the groundwater's contaminated...
Can you explain clay liner?
Clay liner. What do you want me to explain?
What material clay liner?
So bentonite is one of the... Sorry?
Sodium bentonite.
Bentonite is one of the most popular materials. You can use natural clay. You've got to go find the right clay. You look at the properties. Clay has got soil retention property, moisture retention. So it doesn't allow passage of water through it. It becomes impermeable. So any clay material you can use, depending on the type of clay and its resistance to the application. Does it help? So what you do is that when you excavate like this, these are evaporation ponds. Then you come back and you put clay in there. You have to engineer it now. So you've got to compact it. You've got to construct your berms so that these can hold their shape and not have water passing through them, etc., etc. But the point is that it needs lining, and these liners are expensive.
Geomembrane also used for this purpose?
Well, to a certain degree, yes, they can. But geomembranes are still allowing water to pass through them, depending on which one you use. So geomembranes are rather used for control of water distribution, that interface, if you are percolating water through. Yeah, we don't want to allow water to percolate through, we want to have a barrier. So this wind-aided ventilation system is something that's come up where they've said, well, let's use this as an alternative to evaporation fans. And it's really a series of panels where the water's exposed to and the wind blows through them, and it increases evaporation. So you have these big panels that are wet in these desert areas where the dry, hot air is blowing, and we're finding some success with it. I haven't got a hell of a lot of information on it. This is part of what's come out of this paper that I've researched recently. But there's some references to it. I think it's on the next slide. It's not a bulletproof solution. It can also still contribute to groundwater pollution. So you need to still understand that and be aware of it. Depends on your groundwater interface. Groundwater and geological structures under the ground are a topic you can talk on for 2 days on its own. We'll touch on it tomorrow when we talk about primary settling tanks and sludge interface. It might help you put it in perspective in terms of groundwater contamination in a broad scope. So here's some of the results from some of the applications that they've had. So that's significant, in my opinion, relative to just an evaporation pond performance. Up to 90% efficiency. I suppose it's all relative to cost because they're not showing costs here. What is the difference in cost? But bearing in mind that you'll be surprised, evaporation ponds and the lining on an evaporation pond can become quite an expensive little exercise. It certainly reduces the operating footprint, there's no doubt about that. And these can be a lot smaller. And so look at this. They're really starting to apply it in terms of the brine disposal. What was this last one? I think that was just a working example. And that's what it looks like. Maybe I don't know, I don't think I've got an actual photo, but if you want one, I can show you. There's a couple of YouTube videos on it, but the YouTube videos get quite commercial, so I don't like showing them in a class like this because it takes half the video just to get through the commercial side. We're the best and we're this and we're that. But this is the concept of it. So you have these, in fact there is a photograph. No, I haven't got a photograph of an installation. I thought I had one in here. Of these plates, or frames to call it that are wet. Okay, but if you Google wave, you'll find some reference. Not a lot, but it's something that is around.
This is only water showering and air pass, natural air.
So natural draft.
Need any blower?
No. You can probably induce that by putting in blowers, but depending on your efficiencies, do you want more than that? What's the cost associated with blowing air through there as well? What is the efficiency increase in doing that? You need to contemplate all of that.
But if we use blower, air blower, most of the salt particles escape with the air.
Which you don't want because you're distributing it now. It could become contamination. So there's lots of still to contemplate on it. I kind of like the idea. I think it's smart, but again, it's horses for courses. Whatever suits your application, large scale, I'm not sure if this is going to work. But then you look at solar and PV, and that's working at scale now as well, big time. We can start looking at plants and using plants as an option for brine disposal, I suppose. It depends on the types of plants that you want and how you're going to manage those. So obviously low salt tolerance plants are the way to go. And there's these kinds of types of plants, the angiosperms, which there's a whole lot of different fruits that surprisingly enough, and again I'm not an expert in this, but these are all angiosperms, but also other types of crops that are apparently salt tolerant. And so you can grow these crops in the brine and they take up the salt. So a certain amount of angiosperms are halophytes, and we want to get into that too much of these details now, but that's some of them. So, hey, look what's happening. Look what we're starting to introduce now. We haven't yet spoken about energy production. And there's a huge drive towards moving away from fossil fuel energy generation, right? Across the world, and how much of your power has been generated here by coal? In Pakistan, huh?
It's taking up now at the moment. Previously we were very low, less than 1%, but now we have gone up to roughly 10 to 15%. But shortly, within 2 to 3 years, we will be up to 25%.
On coal-fired.
on coal.
So that's going against the trend. So your government is going to get a hiding when they go to the next sustainable.
We woke up later.
Yeah.
But still coal
In
is,
South Africa, we're in denial because we're saying, but we've still got coal, so we're going to use our coal-fired power stations.
next 30 years, still coal is there.
Really?
Yeah.
But you know, the things are moving very fast, and the whole globe is moving towards the renewable.
Yes, that's what we're saying.
So ultimately, solar, wind,
And biofuel, so a waste to energy, I suppose.
Yeah.
Organic waste to energy, even plastics and that you can burn and make energy.
and that's why I was asking you about the regulations in South Africa for the solid waste. Because until and unless we produce energy from the solid waste, there is no solution to the solid waste disposal.
So it's a massive problem, not a problem, a challenge, because the biggest challenge with municipal waste is separation of material.
Yeah.
And you want to separate that at source, which means separation at home. And we haven't, not many places in the world are doing that properly. Even those first world countries that think that they're great, the Germans and the Norwegians and all these guys that are very, very focused around their waste sourcing. I've seen some places in these European countries where they have their separate drums and they're strict. To the point where you go on holiday to a place and in your self-catering apartment, you've got 4 or 5 different bins. And it's all in the basement, the 4 or 5 different bins. So every morning you were to take 5 drums with you, and paper goes there, glass goes there, this goes there, blah, 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 blah.